on to the laws themselves. So, the first series of laws that I will be presenting deal with changing situations where we have a beginning scenario and an end scenario, and we want to know how the values change. The first law is credited to an English gent by the name of Boyle, good English lad, who discovered that pressure is inversely proportional to volume. So he discovered that pressure, if you took a pressure, multiplied it by a volume, and you got a number, changed something, okay, second pressure, second volume, also got a number, that these two relationships here, they were in fact the same, so we could equate them. P1 V1 equals P2 V2. Notice that temperature and moles are not present in this equation, means they cannot change. In this problem, as I mentioned in the introductory video, the unit that you use for pressure or volume does not matter so long as you use the same one. So P1 and P2 must be in the same unit. What is it? Doesn't matter, so long as the problem doesn't specify. Our second law, again, another good English gent by the name of Charles, and he noticed that volume varies with temperature. Don't forget that when we hit absolute zero, all of a sudden all motion stops. So our formula, for Charles's law is V1 over T1 equals V2 over T2. Again, this is a changing situation, so the units do not matter, so long as you use the same unit for V1 and V2. However, temperature, you have no choice. It must be in Kelvin. No ifs, ands, or buts. Pressure and moles are not present in this equation, thus cannot change. If they change, gotta find you a new equation. Next, we have two gentlemen, one with the last name of Gay and the second with the last name of Lusaac, and together they discovered this particular law that noticed the variation of pressure with temperature. So P1 over T1 equals P2 over T2. Again, pressure's units do not matter, so long as they use the same unit for P1 and P2. However, temperature has to always be in Kelvin. Our next one is everybody's favorite. This is the combined gas law. So all we've done is we've taken Boyle's and Charles and gay-Lusaac's and we've mixed them all together. Here's Boyle's right here. That P1 V1 equals P2 V2. Here's our P1 T over T1 P2 over T2. Our gay-Lusaac's law, and here's Charles, V1 over T1, V2 over T2. So all three of our equations are combined in this guy. So that saves you from actually having to memorize all those individual laws. Just remember this one. Anything that does not vary in the equation, you simply omit. So if the problem says that the pressure and volume are a given amount, pressure changes, what is the new volume? Temperature was not mentioned. Scratch it out. Or perhaps if you discover that the temperature remains constant in a particular problem. If it stays constant, mathematically it will not affect the outcome of the problem, and you can omit it. But again, this is for situations in which we have a changing scenario. So, beginning and an end, something changes. Pressure and volume units do not matter so long as they are consistent. Temperature, however, must always be in Kelvin. Almost finished with the laws. The next one is Avogadro's law. This is the same gentleman that brought you 6.02 times 10 to the 23rd things per 1 mole. Same guy. This is actually what he was better known for, was his work with gases. And he noticed how volume varies with your amount, specifically in moles. So again, volume units irrelevant unless the problem specifies, so long as they are the same. N, however, must be in moles. Now, personally, I always get this equation upside down. I never remember which one goes on top, the N or the V. But as long as you are consistent like this, both V's are on the top or both N's are on the top, your relationship is still the same. Let's see. Last law for now, before we go through a couple of examples. There it is. Let's see if I can keep my paper from falling off. Whoops. Is Dalton's law of partial pressures. That's the full name. And Dalton's law of partial pressures says that the total pressure in a system is the sum of the individual pressures. So PT stands for P total is P1 plus P2 plus P3. It really is that simple. So for example, in a combustion reaction such as you see at the bottom there, that's methane combusting or reacting with oxygen gas to produce carbon dioxide and water vapor. All four of those are gases. So if I put that in a box and close the box and let that happen in the box, my total pressure in the box would be the sum of whatever CH4 is left over, whatever oxygen is left over, whatever CO2 I made, plus whatever water vapor that I made. So all of those individual pressures added together. So let's see. I've got 5 minutes left before I hit my YouTube limit. Let's try a couple of these types of problems. So this is a worksheet that I hand out in my class. If this is one of my students watching this, sorry, this will look a little bit familiar to you, but hopefully the review will help nonetheless. If you're not in my class, you have no idea what this is, in which case, yay, something new. All right, couple of examples. A recommendation I always make to my students is that if you don't know where to begin, start by underlining what looks useful. So if we look at this problem here, if we look at number 1, a gas is at 735 torr, 323 Kelvin, and 21 liters. Hopefully you can read that. It's kind of small. Conditions change to 1 atmosphere and 27 degrees Celsius. What is the new volume? So, stuff that looks useful. Numbers always look useful. That looks useful. That looks useful. Here's the big word. My conditions change. That's what tells me that I'm going to use one of those laws that we just talked about. Here's my new conditions. What is the new volume? Next thing we want to do is to convert these into more familiar variables. Torr was one of our units for pressure. Since I'm changing, I'm going to have a P1 and a P2. Gosh darn flower. P1 is in torr. P2 is in atmospheres. That's not good. We're going to have to convert one or the other into the same unit. It does not matter which way you go, again, so long as you are consistent. Personally, I'm a big fan of atmospheres. So 760 torr is 1 atmosphere, so 735 divided by 760. Let's see, I have a temperature. Now, degrees Celsius is never okay. It must be in Kelvin, so adding 273 gives me 300 degrees Kelvin. Degrees Kelvin, I think that's right. My initial volume is 21, and they're asking me for my change in volume. I like to write the variables side by side like this because it makes it easier for me to notice when something is staying the same. I can just look across the board and see which variables are constant, which variables are changing, which ones am I missing. So since I have all three of these, I'm going to need to use the combined law. Another recommendation that I make to my students is to rearrange the equation in variable form like this before you start adding in numbers. Once you start trying to rearrange numbers, you increase the likelihood that you're going to make a silly mistake. Move a decimal the wrong way, drop a zero, have a moment where you switch around numbers. So we're looking for this V2. We got to get that V2 by itself. So T2 is being divided here. I'm going to multiply both sides by T2. P2 is being multiplied here, so I got to divide both sides by 1 over P2. I rewrite that over here. So now we can just plug in our numbers and hit equal on our calculator. So let's see. P1 is 0.967 atmospheres. V1 is 21. T2 is 300. T1 is 323 times P2 is 1 atmosphere. That gives me a new volume of 18.861 liters. Since this side was in liters, my answer will also come out in liters. How many sig figs can I have? Oh dear. Maximum of 2. So my volume has decreased. Volume has decreased. That should make some sense if you think about the kinetic molecular theory. If you look at our temperature, it has decreased. Decreased temperature implies that my molecules have less energy to bounce into the walls and keep that balloon expanded, if you will, and so it does, in fact, shrink. How much time do I have? Oh, goodness, I am out of time. Check out the next video for a few more samples on how to work these problems.